The findings of the James Webb Space Telescope have undermined the case for the Big Bang. The James Webb Space Telescope has just delivered a thrilling discovery that is sending shock waves through the world of physics. Through a single breathtaking image, it has destroyed long-standing debates, leaving scientists stunned. The era of speculation is over, as Webb's latest capture is both visually captivating and a game-changer that promises to revolutionize our perception of reality. What fiery debate among scientists has this image decisively ended? In what ways is the stunning image captured by the James Webb Space Telescope redefining our understanding of the cosmos? Join us as we delve into why James Webb's findings are putting an end to debates in physics with a shattering image. The fundamental issue with astrophysics is that scientists can't come to an agreement about how old the universe is or how fast it is expanding. This unanswered phenomenon has puzzled scientists across generations, leading them to conduct various research to find answers. Cosmology is the field of research that focuses on understanding how the universe was created, how it is put together, how it has changed over time, and ultimately how it will end. This field has witnessed significant development in the past 100 years. The currently accepted cosmology model, the Big Bang theory, suggests that the universe has been expanding from a very hot and dense initial state for about 13.8 billion years. This expansion is measured by the Hubble constant, which indicates the speed at which the universe is expanding. However, measurements of the Hubble constant are not straightforward. Measuring the Hubble constant can be broadly categorized into two groups: local measurements and early universe measurements. Local measurements involve the study of the astronomical bodies of the universe. For example, Cepheid variable stars and Type Ia supernovae serve as standard candles to measure the Hubble constant due to their brightness. Using their luminosity, astronomers can measure how the universe's expansion affects the speeds of these objects to deduce their distances and thus calculate the Hubble constant. The second group is the measurement of the early universe. Scientists use observations of the cosmic microwave background radiation, CMB, the afterglow of the Big Bang, which was discovered in the 1960s. The CMB displayed the microwave radiation of the early universe when it was just 380,000 years old. By measuring the tiny temperature and polarization radiated by the CMB, astronomers can establish the age of the universe and its rate of expansion. But here's the problem. The results of these two methods do not correlate. The results observed through local measurements confirm that the universe is expanding faster than what we estimate based on CMB data. Due to these differences, scientists have been working hard to uncover the reason behind the results. As such, further research is being conducted to learn more about the mysteries of the universe. As things stand, the difference in measurements shows that there is either new science we don't know about yet or mistakes in one or both ways by which we are measuring things. Thanks to the James Webb Space Telescope, we can see into the dark cosmos clearer than ever before. The telescope can display the faintest and most distant elements, planets, and galaxies we would not have thought it was possible to see. Due to its abilities, scientists naturally assumed that data from the JWST would assist us in precisely calculating the Hubble constant. However, the first wave of data has remarkably made matters more complicated. They have given us new insights that are not coherent with what we thought we knew. Could this data lead to a new theory and revolutionize how we think about space? If so, we might need to review our understanding of how the universe works. For instance, we may discover particles and forces that have never been observed before, or it could signify that dark energy, an unknown factor responsible for the accelerating expansion of our universe, needs to be re-examined. So far, the ways we think about space have evolved as we continue to discover new things. For example, in 1965, when researchers discovered the cosmic microwave background radiation, it served as strong evidence for the idea of the Big Bang theory. Before then, scientists thought that the universe was eternal and hence was constantly expanding at a uniform rate, but the new evidence proved that was not the case. Also, when we found out towards the end of the 1990s that the universe was continuously expanding at an accelerating rate, it further changed our understanding. We discovered dark energy and its influence on the universe's expansion. Thus, every time we learn something new, we question whether it fits into our current frame of work. If not, we come up with new approaches to understand the universe better. To this end, The issue we are facing in cosmology today might lead to the discovery of the most wonderful solutions to the universe. While the issue is challenging, it is also exhilarating as it compels us to develop more technologically advanced tools to explore space. This cosmological dilemma also unites the scientific community from different countries, as every scientist wants to know more about the universe. Most importantly, it shows that science is constantly changing and growing as we learn more about space. Along with the Hubble tension, there is also a concern known as the S8 tension. This is with regard to the spatial distribution of matter in the universe. This can be used to draw a structural picture of the universe and see how it has evolved. The astronomers refer to this phenomenon as lumpiness. This is because there are areas of space that have lots of galaxies closely grouped while other areas are sparse. The scientists will use different techniques to measure this lumpiness, and one way is to look at how the light from distant galaxies gets bent by the different gravity of big objects such as galaxy clusters. This bending, known as gravitational lensing, provides us with a way to investigate where dark matter is, given that it is invisible as it does not emit light. Researchers also use the cosmic microwave background, CMB, an afterglow from the beginning of the Big Bang. This light has been in motion for approximately 13.8 billion years, bearing news from the early universe. Through the CMB analysis, physicists are able to decode how the universe was lumpy in its birth, which should match the observational lumpiness of the universe at the present time on a large scale. But here's the catch. These results also don't align. The CMB's lumpiness, presented by the non-spherical gravity distribution model, implies that the matter distribution at the early stage of the universe was more homogeneous compared to the one observed using gravitational lensing. As such, we can guess that there is something else that we are not considering in the explanation. This brings us back to the concept of dark matter. What exactly is dark matter, and how does it operate? The truth is, the question remains unanswered. However, all hope is not lost, as the James Webb Space Telescope, JWST, is set to redefine the field of astronomy with its unprecedented high resolution and camera sensitivity. The telescope will examine early eras of the universe and investigate the first galaxies and stars formed. This makes it possible to improve measurements of cosmic expansion and matter distribution. These critical questions will need precise observation and possibly new approaches from a theoretical perspective to figure them out. Regardless of whether the end is finding more meaning to dark energy, discovering completely new physics, or even gaining a better understanding of dark matter's behavior, the implications will be far-reaching. Tackling the mysteries of the universe is like working out a zillion-piece puzzle blindfolded. Scientists can be seen as thorough detectives who are focused on and obsessed with solving these mysteries. The latest venture, called Project Flamingo, is proof of NASA's intensifying passion for scientific exploration. Using one of the world's most highly acclaimed supercomputers situated at Durham University in Britain, Project Flamingo is an absolutely spectacular feat in the world of computational progress. It costs more than $50 million hours of computer time and features 30,000 processors and counting. The exercise highlights the scientific community's resolution to explore the universe in its entirety, majorly focusing on dark matter. Dark matter, the mysterious substance that neither emits, absorbs, nor reflects light, is inferred to exist due to its gravitational influence on visible matter. Its elusive nature continues to intrigue scientists. However, the approach of Project Flamingo is different from previous simulations. It involves all possible forms of cosmic elements, from galaxies of the most different gas content to stars and black holes at the center of the universe. Through such a systematized method, the gradual shift in the representation of the universe was created from a basic landmark sketch. The motivation behind ambitious endeavors like Project Flamingo is clear: to clarify cosmic conflict where the measurements seem to be faulty and do not fit into the structure of the universe. This disparity in measurement suggests a fundamental misunderstanding in our current comprehension of the universe's workings. If these metrics can be compared to musical genres, they are similar to jazz and classical, each having its own technique although still related. Flamingo attempts to unite these divergent views and sharpen our individual perceptions of the cosmos. However, despite its sophistication, the cosmic tension persisted. This tension continues to exist as humbling evidence that we have yet to solve much of the mystery that surrounds us. The universe seems unwilling to trade its secrets with us just like that. As we add each new data point and simulation model to our toolbox, like Flamingo, an increasingly vast new universe opens up with new issues to address. That is a never-ending quest where every answer leads to more questions, opening up a whole new layer to it. It shows us that the nature of our pursuit to unravel the universe's mysteries is intricate and always changing. Since the moment Edwin Hubble made his sparkling discovery of the expanding universe in the early 20th century, the speed of our comprehension has been astoundingly fast. Scientists are consistently making different discoveries about the dimensions of the world, such as the Big Bang theory, dark matter, and dark energy. They have investigated the galaxy by examining the cosmic microwave background and figuring out the distance of celestial bodies. Regardless of all that, there remain a lot of unfilled pieces to the puzzle, missing measurements, cosmic tensions, and an endless wealth of questions. Each step forward brings with it a dizzying and often humbling realization of the universe's complexity. Science is, by nature, an ever-evolving domain. Each discovery we make is like a step in a dance with the cosmos. Every twirl, every move leads us closer to unlocking its mysteries. The James Webb Space Telescope's latest findings are just another move in this infinite dance. These discoveries shake our understanding and push us to rethink everything. In conclusion, we can confidently say that the field of cosmology is not defined by static truths but by the dynamic, ongoing, relentless pursuit of knowledge. It is filled with thrilling discoveries and reshaped theories. It is a field that continually demands us to look deeper, think harder, and remain ever curious. As we continue to explore the farthest reaches of space, we can be sure that more fascinating revelations and more profound mysteries await us. And so, the cosmic dance goes on, ever more intriguing and infinitely awe-inspiring.